In this video, we will study a particle swarm optimization-based maximum power point tracking algorithm, also known as PSO MPPT, and implemented in MATLAB and Simulink. We will first understand the basic concept of maximum power point tracking, then explain the particle swarm optimization algorithm and its mathematical equations. Finally, we will move to Simulink and examine the complete PSO MPPT implementation, including the initialization process, particle movement, power measurement, global best selection, duty cycle generation, and PWM control. A photovoltaic panel does not always operate at its maximum available power. The output power of a PV system depends on several factors, including solar irradiance, temperature, and the electrical operating point of the panel. The PV power is calculated as voltage multiplied by current. Therefore, the objective of an MPPT controller is to continuously adjust the operating point of the photovoltaic system so that the extracted power approaches the maximum available power. This maximum operating point is known as the maximum power point, or MPP. If we plot the PV power against the PV voltage, we obtain a nonlinear power voltage characteristic. There is normally one operating point where the PV power reaches its maximum value. This point is called the maximum power point. Mathematically, at the maximum power point, the derivative of power with respect to voltage is equal to 0. The MPPT controller therefore has the task of finding this operating point and keeping the PV system close to it. There are many techniques available for maximum power point tracking. One of the most popular methods is perturb and observe, where the controller slightly changes the operating point and observes whether the power increases or decreases. Another technique is incremental conductance, which uses the relationship between the incremental and instantaneous conductance. More advanced approaches include fuzzy logic, neural networks, and optimization algorithms. In this video, we focus on particle swarm optimization, or PSO. Particle swarm optimization is a population-based optimization algorithm inspired by the collective behavior of groups of animals, such as birds flocking or fish schooling. Instead of searching for a solution using only one point, PSO uses several particles. Each particle represents a possible solution to the optimization problem. In our MPPT application, the position of a particle represents a candidate duty cycle for the DC-DC converter. The objective is to find the duty cycle that produces the highest PV power. In our implementation, we use 3 particles. Every particle has a position and a velocity. The position represents the current duty cycle. Each particle also remembers the best position it has personally found. This is called the personal best, or P-best. At the same time, the entire swarm remembers the best solution found by any particle. This is called the global best, or G-best. The particles then use both their personal experience and the experience of the entire swarm to determine their next position. The first major equation in particle swarm optimization is the velocity update equation. The new velocity consists of 3 components. The first component is the inertia term. It encourages the particle to continue moving in its current direction. The second component is the cognitive term. It attracts the particle toward its own personal best position. The third component is the social term. It attracts the particle toward the global best position found by the entire swarm. These 3 components allow the particles to explore the search space and gradually converge toward a promising solution. After calculating the new velocity, we update the position of the particle. In our application, the particle position is the converter duty cycle. Therefore, the new duty cycle is equal to the current duty cycle plus the new particle velocity. The particles repeatedly perform this process, evaluate the resulting PV power, update their personal best, update the global best, and then move again. Now we can formulate the MPPT problem as an optimization problem. The PV power is a function of the converter duty cycle because changing the duty cycle changes the operating point of the PV system. Therefore, PSO searches for the duty cycle that maximizes the product of PV voltage and PV current. In mathematical terms, We want to find the duty cycle corresponding to the maximum value of PV power. This is the central idea behind PSO-based MPPT. In our Simulink implementation, the swarm contains 3 particles. The inertia coefficient is set to 0.4. The cognitive coefficient is 0.8, and the social coefficient is 1.22. We also use fixed values of 0.25 for the 2 scaling factors. Therefore, the effective cognitive coefficient is 0.2, while the effective social coefficient is 0.305. The optimization process is performed for 10 iterations. Because of the parameter values used in our MATLAB function, the general PSO equation can be simplified. The new velocity is equal to 0.4 times the previous velocity, plus 0.2 times the distance between the personal best and the current duty cycle, plus 0.305 times the distance between the global best and the current duty cycle. After calculating the velocity, the new duty cycle is obtained by adding the velocity to the current duty cycle. We will now see exactly how these equations are implemented inside Simulink. The complete PSO MPPT process can be summarized in 10 steps. First, we initialize the particles with different duty cycles. Then each particle is applied to the converter and the resulting PV voltage and current are measured. The PV power is calculated using voltage multiplied by current. The personal best and global best values are then updated. The PSO velocity equation is used to calculate a new particle position. This process continues for several iterations. Finally, the best duty cycle found by the swarm is used as the MPPT operating point. Once PSO finds the best duty cycle, this duty cycle must be applied to the power converter. The global best duty cycle is first passed through a saturation block. It is then sent to the PWM generator. In our model, the PWM switching frequency is 50 kHz. This corresponds to a switching period of 20 microseconds. The PWM signal then controls the switching device of the DC-DC converter. Several different timescales are used in the Simulink model. The initialization sequence has a sample time of 1 millisecond. The iteration sequence has a sample time of 10 milliseconds. The delay block uses a sample time of 50 microseconds. The zero-order hold has a sample time of 100 microseconds. Finally, the PWM operates at 50 kHz, corresponding to a 20 microsecond switching period. This separation between the fast PWM dynamics and the slower MPPT optimization process is important for proper operation. We have now covered the theoretical foundation of PSO-based MPPT. Let's move to MATLAB Simulink and examine how these equations are implemented in the actual model. We will start with the initialization sequence and then follow the particles through the optimization process until the final duty cycle is generated for the PWM controller. This Simulink model shows a PV boost converter system controlled by a particle swarm optimization-based MPPT algorithm. Starting from the PV array, its output feeds a boost converter made up of an input capacitor C1, an inductor L, a switching MOSFET, a diode, and an output capacitor C2. A resistive load is connected at the output, along with current and voltage sensors, IOUT and VOUT, used to compute the output power, POUT. On the input side, the model measures the PV voltage, VIN, and PV current, IN. These two signals are multiplied together to calculate the instantaneous PV power, PPV. The VIN and IN measurements are then fed into the PSO MPPT block. This block runs a particle swarm optimization algorithm to search for the duty cycle, D, that drives the converter toward the PV array's maximum power point. Rather than following a fixed gradient like perturb and observe, PSO treats the duty cycle search as an optimization problem, iterating a swarm of candidate solutions to converge on the optimal operating point, even under partial shading conditions. The resulting duty cycle, D, is sent out to control the switching of the MOSFET, closing the feedback loop between the measured power and the converter's operating point. This is the complete PSO-based MPPT subsystem implemented in MATLAB Simulink. The main component is the embedded MATLAB function containing the PSO algorithm. Around this function, we have the initialization sequence, iteration sequence, delay block, voltage and current measurements, zero-order hold, saturation, and PWM generator. Let's examine each part step by step. We begin with the initialization sequence. This sequence generates the values 1, 2, 3, and 4 with a sample time of 1 millisecond. The first 3 values are used to initialize the 3 particles. The fourth value indicates that initialization has finished and the PSO optimization stage can begin. Therefore, this block controls the transition between initialization and optimization. Inside the MATLAB function, the initialization signal is received through the input labeled Q. When Q equals 1, the first particle is initialized with a duty cycle of 0.05. When Q equals 2, the second particle is initialized with a duty cycle of 0.45. When Q equals 3, the third particle is initialized with a duty cycle of 0.95. The initial particle positions are therefore 0.05, 0.45, and 0.95. Their initial velocities are set to 0. When Q reaches 4, the variable W is set to 1. This is the transition point between initialization and optimization. Before this point, the algorithm is assigning the initial duty cycles to the particles. After this point, the PSO velocity and position equations become active. In other words, W acts as a mode selector between initialization and the optimization process. After initialization, the iteration sequence generates 1, 2, and 3 repeatedly. This signal is connected to the input labeled I of the MATLAB function. The value of I determines which particle is currently being processed. Therefore, the algorithm updates particle 1, then particle 2, then particle 3, and then starts the sequence again. The iteration signal is also passed through a delay block to generate the signal labeled B. This delay is important because after changing the converter duty cycle, the PV system needs some time to respond. We should not change the duty cycle and immediately evaluate the power at the same instant. The delay provides synchronization between applying a particle's duty cycle and evaluating the resulting PV power. Therefore, the input I determines which particle is being processed, while the delayed signal B indicates which particle's power should be evaluated. The MATLAB function also receives the PV voltage and PV current through the inputs labeled V and I. These two signals are used to calculate the instantaneous PV power. The power calculation is simply P equals V multiplied by I. This measured power is the objective function used by the PSO algorithm. A particle that produces a higher PV power becomes a more promising candidate for the maximum power point. The algorithm stores 2 important quantities for every particle. The first is its best power found so far, called the local best power. The second is the duty cycle that produced this power, called the local best duty cycle. Whenever the current particle produces more power than its previous personal best, the algorithm updates both values. In this way, every particle remembers its own best experience. In addition to the personal best of each particle, the algorithm maintains a global best. The global best represents the highest power found by the entire swarm. When a particle's personal best becomes greater than the current global best, the global best power and its corresponding duty cycle are updated. Therefore, the global best represents the most promising operating point discovered by all 3 particles. Now we reach the main PSO calculation. This line calculates the new velocity of the particle. The velocity contains 3 components. The first component is the inertia component, which depends on the previous velocity. The second component attracts the particle toward its personal best duty cycle. The third component attracts the particle toward the global best duty cycle. In our implementation, the resulting equation is V equals 0.4 times the previous velocity, plus 0.2 times the difference between personal best and current duty cycle, plus 0.305 times the difference between global best and current duty cycle. After calculating the new velocity, the current duty cycle is updated. The new duty cycle is equal to the previous duty cycle plus the new velocity. Therefore, the particle moves through the duty cycle search space. If the global best is located at a higher duty cycle, the social component tends to push the particle upward. If the global best is located at a lower duty cycle, the particle is pushed downward. This process allows the swarm to gradually concentrate around the region of maximum power. The output labeled D1 represents the current particle duty cycle generated by the PSO algorithm. During optimization, different particles produce different duty cycle values. These values are used to explore different operating points of the photovoltaic system. The second output is D2. D2 represents the global best duty cycle found by the PSO algorithm. Whenever a particle produces a new maximum power, the global best duty cycle is updated. Therefore, D2 represents the best-known operating point of the swarm at that moment. The global best duty cycle then passes through a zero-order hold block. The sample time of this block is 100 microseconds. The purpose is to hold the duty cycle constant between updates. This prevents the PWM reference from changing continuously and ensures that the converter receives a stable duty cycle command for a defined period. Next, the duty cycle passes through the saturation block. The lower limit is 0.1 and the upper limit is 1. Therefore, the duty cycle applied to the PWM is constrained between 0.1 and 1. This prevents the PSO algorithm from generating an invalid PWM command outside the allowed operating range. Finally, the duty cycle command enters the PWM generator. The switching frequency is 50 kHz. Therefore, the switching period is 20 microseconds. The PWM generator converts the duty cycle command into the gate signal required by the power electronic switch. For example, a duty cycle of 0.5 corresponds to approximately 50% of the switching period being in the active state. It is useful to compare the different timescales in this model. The PWM switching period is 20 microseconds. The zero-order hold period is 100 microseconds, which corresponds to 5 PWM switching cycles. The particle iteration period is 10 milliseconds. Therefore, each particle is given a much longer time compared with the switching period before the optimization sequence moves to the next particle. This allows the converter and photovoltaic system to respond to the applied duty cycle before the power is evaluated. Let's summarize the complete signal flow. First, the initialization sequence creates the initial duty cycles for the 3 particles. After initialization, the iteration sequence selects particles 1, 2, and 3. Each particle is applied to the converter. The resulting PV voltage and current are measured, and the PV power is calculated. The algorithm compares the measured power with the particle's personal best. It then updates the global best if necessary. Using the personal best and global best positions, the PSO algorithm calculates a new velocity and a new duty cycle. The global best duty cycle is then passed through the zero-order hold and saturation blocks and finally sent to the 50 kHz PWM generator. The PWM signal controls the DC-DC converter, which changes the PV operating point. This feedback process allows the PSO algorithm to search for the maximum power point. This part of the model represents the PV array subsystem, built from 9 individual PV modules arranged in a 3x3 series parallel configuration. Each module receives irradiance, G, and temperature, T, as inputs, with bypass diodes connected across each module to protect against mismatch and partial shading losses. The array terminals, PV+ and PV- connect to the rest of the boost converter circuit. Temperature is held constant at 25 degrees Celsius throughout the simulation. Irradiance, however, is varied using a step-based signal, changing from 1000 to 500 to 800 watts per square meter at time instance 0, 0.05, and 0.1 seconds respectively. This setup tests how well the PSO MPPT algorithm can reacquire the maximum power point when the PV array's operating conditions suddenly change. Now, looking at the scope results, 3 signals are plotted together, pouting yellow, the PSO MPPT duty cycle in blue, and PPV in orange. At the start of the simulation, with irradiance at 1000 watts per square meter, the PSO algorithm begins searching, causing the oscillations visible in PPV during the first few milliseconds as the particles explore different duty cycle values. Within about 20 milliseconds, the algorithm converges and both PPV and POUT settle around 1000 watts, confirming that the true maximum power point has been found. At 0.05 seconds, irradiance suddenly drops to 500 watts per square meter. PPV dips sharply and the PSO MPPT algorithm reacts, driving the operating point down to track the new, lower maximum power available from the array. After a brief transient, the power stabilizes around 650 watts, matching the reduced irradiance level. At 0.1 seconds, irradiance rises again to 800 watts per square meter. PPV shows a spike as the algorithm readjusts, followed by a short oscillation before settling around 800 watts, again matching the new operating condition. Throughout all three irradiance steps, POUT closely follows PPV with only a small tracking delay, showing that the boost converter efficiently transfers the power extracted from the PV array to the load. Overall, these results confirm that the PSO MPPT algorithm successfully reacquires the maximum power point each time the irradiance changes, demonstrating strong dynamic tracking performance under varying environmental conditions. And that brings us to the end of this tutorial on PSO-based maximum power point tracking in MATLAB and Simulink. I hope this video helped you understand how particle swarm optimization works and how it can be applied to extract the maximum available power from a photovoltaic system. If you found this video useful, please give it a like, share it with your friends and colleagues, and subscribe to the channel for more tutorials on MATLAB, Simulink, power electronics, renewable energy, and advanced control systems. And don't forget to turn on the notification bell so you don't miss the next video. If you have any questions, suggestions, or topics you'd like me to cover in future videos, feel free to leave a comment below. Thank you very much for watching, and I'll see you in the next video. Take care and keep learning.